Account Abstraction. Please note that with the system update of February 2023, the ARX concept is only used by the VM, while the API layer operates with gas. For more information, read the changelog. Introduction. On Ethereum, there are two types of accounts: the externally owned account and the contracts account. The former type is the only one that can initiate transaction, while the latter is the only one that can implement arbitrary logic. For some use cases, like smart contract wallets or privacy protocols, the difference can create a lot of friction, and as a result of such applications, require layer 1 relayers like an EOA to help facilitate the transaction from a smart contract wallet. Accounts in the Zksync era can initiate transactions like an EOA, but they can also have arbitrary logic implemented into them like a smart contract. This feature is called Account Abstraction, AA. It aims to resolve the issues described above. Note: the Zksync era is the first EVM-compatible chain to implement native account abstraction. We're evaluating how well the implementation works with EVM projects on testnet and mainnet. No incompatibilities have been found so far. Due to the early stage nature of the future, you may see some breaking changes to the account abstraction API interfaces. However, given that the account are version in the Zksync era, older accounts will work even after breaking changes are released. Native account abstraction Native account abstraction on Zksync era fundamentally changes how accounts operated by introducing the concept of smart contracts and accounts, smart accounts and paymasters. Smart accounts are fully programmable, allowing for various customizations, such as signature schemes, native multi-sig capabilities, spending limits, and application logic specific restrictions. Info: the native account abstraction of Zksync and Ethereum EIPs 4337 aim to enhance accounts flexibility and user experience, but they differ in key aspects. Paymaster, conservatively, can sponsor transactions for users, enable them to pay transaction fees in ERC20 tokens. This innovative approach to account management significantly enhances the user experience, security, flexibility, paving the way for a broader adoption. Prerequisites: to better understand this page, recommend you first read their guide on accounts. Design: the account abstraction protocol on Zksync is very similar to EIP 4337, though our protocol is still different for the sake of efficiency and better UX. Keep nonces unique. The current model does not allow for custom wallets to send multiple transactions at the same time and maintain deterministic ordering. For EOAs, nonces are expected to grow sequentially, while custom accounts, the order of transactions cannot be guaranteed. In the future, we plan to switch to a model where accounts can choose between sequential and arbitrary nonce ordering. One of the important invariants of every blockchain is that each transaction has a unique hash. Holding this property with an arbitrary account is not trivial, though accounts can, in general, accept multiple identical transactions, even though those transactions will be technically valid by the rules of the blockchain. Violating hash uniqueness would be very hard for indexers and other tools to process. There needs to be a solution on the protocol level that is both cheap for users and robust in case of a malicious operator. One of the easy ways to ensure that transaction hashes do not repeat is to have a pair, sender nonce, always unique. The following protocol is used. Before each transaction starts, the system queries the nonce holder to check whether the provided nonce has already been used or not. If the node has not been used yet, the transaction validation is run. The provided nonce is expected to be marked as used during this time. After the validation, the system checks whether this nonce is now marked as used. Users will be allowed to use any 256-bit number as nonce, and they can put any non-zero value under the corresponding key in the system contract. This is already supported by the protocol, but not on the server side. More documentation on various interactions with the nonce holder system contract as well as tutorials will be available once support on the server is released. For now, It is recommended to only use the incremental nonce if equals method, which practically enforces the sequential ordering of nonces. Standardizing transaction hashes. In the future, is planned to support it is planned to support efficient proofs of abstractions, including on Zksync. This would require us to calculate transactions hash in the bootloader. Since these calculations won't be free to the user, it's only fair to be included in the hash in the interface of the AA methods, in case the accounts may need to evaluate for some reason, may need the value for some reason. That's why all methods of the iAccount and iPaymaster interfaces, which are described below, contain hash of the transaction, as well the recommended signed the digest that is signed by the UAs for this transaction. Now let's take a look at the interfaces. iAccount interface. Each account is recommended to implement the iAccount interface. It contains the following 5 methods. Validate transaction is mandatory and will be used by the system to determine if the AA logic agrees, if the account abstraction logic agrees to proceed with the transaction. In case the transaction is not accepted, like if the signature is wrong, the method should revert. In case the call succeeds, the implemented logic is considered accepted in the transaction, and the system will proceed with the transaction flow. Execute transaction is mandatory and will be called, next method, execute transaction is mandatory and will be called by the system after the fee is charged from the user. This function should perform the execution of the transaction. Next method, pay for transaction, is optional and will be called by the system if the transaction has no paymaster. Example, the account is willing to pay for the transaction. The method should be used to pay for the fees by the account. Note, if your account will never pay any fees and will always rely on the paymaster, you don't have to implement this method. This method must send at least the XCAS price times the XCAS limit to if to the bootloader address. Prepare for Paymaster is optional and will be called by the system if the transaction has a paymaster. Example, there's a different address that pay transactions fees for the user. This method should be used to prepare for the interaction with the paymaster. One of the notable examples where it can be useful is to approve ERC20 tokens for the paymaster. Execute transaction from outside. Technically not mandatory, highly encouraged, since there's a need to be in some way. In case of priority mode, example, if the operator is unresponsive, should be able to start a transaction for your account outside basically this fallback, the standard ethereal approach where an EOA start the transactions from your smart contract. Now let's look at the iPaymaster interface. Like an EIP for 337 or Account Abstraction Protocol supports paymasters, accounts that can compensate other accounts' transactions execution. You can read more about them here. Each paymaster should implement the iPaymaster interface. It contains the following 2 methods. Validate and pay for paymaster transaction is mandatory and will be used by the system to determine if the paymaster approves for paying for this transaction. If the paymaster is willing to pay for this transaction, this method must send at least gas price time gas limit to the operator, and it should return contest that will be one of the call parameters to the post-transaction method. Post-transaction is optional and is called after the transaction execute. Note that unlike EIP 4337, there is no guarantee that this method will be called. In particular, this method won't be called if the transaction fails with out-of-guise error. It takes 4 parameters: the context returned by validating pay for paymaster transaction, the transaction itself, a flag that indicates whether the execution succeeded, and the maximum amount of gas the paymaster might be refunded with. Reservoir fields of the transaction struct with special meaning. So fields that are reserved. Note that each of the methods above except the transaction struct While some of its fields are self-explanatory, there are six reserved fields that meaning the meaning of each field is defined by the transaction type. We decide not to give these field names since they might be needed in some future transaction type. For now, the convention is reserved 0 is the nonce, reserved 1 is the message value. Transaction flow. Each transaction goes through the following flow: the validation step. During the validation step, the account should decide whether it accepts the transaction and if so, pay the fees for it. Any part of the validation fails, the account is not charged the fee and such transaction cannot be included in the block. Step 1. The system check if the nonce of the transaction has not been used before. You can read more about that. Step 2. System calls the validate transaction method for the account, does not revert, proceeds to next stage. Step 3. The system checks that the nonce of the transaction has been marked as used. Step 4. When no paymaster, system calls the pay for transaction method for the account and it does not revert, proceeds to the next step. Step 4. With paymaster, system calls the prepare for paymaster method. If this call does not revert, then the validate and pay for paymaster transaction method of the paymaster is called. That does not revert to, proceed to next step. Step 5. The system verifies that the bootloader has received at least tax price, transaction price, gas price times transaction gas limit ether to the bootloader. This is the case, the verification is considered complete and we can proceed to the next step. The execution step. The execution step is considered responsible for the actual execution of the transaction, sending the refunds of any unused gas back to the user. If there's any reverts on the step, the transaction will still be considered valid and will be included in the block. System calls the execute transaction method of the account. Step 6. System will call the execution transaction method of the account. Step 7. Only in case of transaction has a paymaster, the post-transaction method of the paymaster is called. This step should typically be used for refunding the sender and unused gas in the case that the paymaster was used to facilitate paying the fees in ERC20 fees. In EIP 4337, you can see three types of gas limits: Asian gas, fusion gas, verification gas, that describes the gas limit for different steps of the transaction included in the block. Zksync era has only a single field, gas limit, that covers the fee for all three. When submitting a transaction, make sure that gas limit is enough to cover verification, paying the fee, and the actual execution itself. By default, calling estimate gas adds a constant to cover the charging fee, the signature verification, always. Let's read that again. By default, calling estimate gas adds a constant to cover charging the fee in the signature for each accounts. Using system contracts caller library. For the sake of security, both the nonce holder contract deploy system contracts can only be called with a special flag, the system flag. You can read more about it here. To make a call with this flag, the system call with propagate revert, system call with revert data methods of the system contracts call library should be used. Using this library is practically a must when developing custom accounts, since the only way to call non-view methods of the nonce holder system contract. You have to use this library if you want to allow users to deploy contracts on the and use this implementation of an EOA account. As referenced, extend the EIP for 337. Provide DOS protection for the operator. EIP 37 imposes several restrictions on the validation step of the account. Most of those regarding forbidding opcodes are still relevant. However, several restrictions have been lifted for better UX. Extending allowed opcodes. It is allowed to call, delegate call, and started call contracts that were already deployed. Unlike Ethereum, we have no way to edit the code that was deployed or delete the contract via self-destruct. So we can be sure that the code during the execution of the contract will be the same. Extending the set of slots belong to a user. In the original EIP, the validate transaction step of account abstraction allows the account to read only store a slot on its own. However, there are slots that are semantically belong to the user but are actually located on another contract address. A notable example is the ERC20 balance. This limitation provides a DDoS safety by ensuring that the slot used for validation by various accounts do not overlap. So there's no need for them to actually belong in the account storage. To enable reading the user's ERC20 balance or allowance on the validation step, the following slots will be allowed for an account with an address A on the validation step. Slots that belong for address A, slots A on any other addresses, slots of type kcheck A or X on any other addresses to cover mapping address value, which is usually used for balance in ERC20 tokens. What could be allowed in the future? In the future, we might even allow time bounding transactions, allow checking that block timestamp is smaller or equals value. If returned false, this will require deploying a separate library such as trusted methods, but will greatly increase the capabilities of the accounts. Building custom accounts. As already mentioned before, above, each account should implement the iAccount interface. An example of the implementation of the account abstraction interface is the implementation of an UA account. Note that this account, just like a standard UA, successfully returns empty when called by external address, while it may not be the behavior you would expect you would like for your account. EIP 1271. If you are building a smart wallet, we highly encourage you to implement the EIP 1271, the signature validation scheme. This is the standard endorsed by Zksync team and is used for signature verification library described below section. The deployment process. The process of deploying an account logic is very similar to the one of deploying a smart contract. In order to protect smart contracts that do not want to be treated as account, a different method of the deployer system contract should be used. Instead of using create2, they should use create account and create to account. Let's take a look on how that works with the Zksync Web3 SDK. So pretty much what's happening here is we're loading the create account factory. And after create account, new contract factory, create account, contract factory deploys. So he will deploy the create account. Awesome. This is the bytecode for the contract for the smart account, and we will be deploy using create account. Limitations of the verification step. The verification rules are not yet fully enforced. Even if your custom account works at the moment, it could stop working in the future if it do not follow the rules below. Very important for audits, huh? In order to protect the system from a DOS track, the verification step must have the following limitations. The account logic can only touch slots that belong to the account. The account logic cannot use context variables like block number. It is also required that your account increases bounce by 1. This restriction is only needed to preserve the transaction hash collision resistance. Transactions that violate the rules above will not be accepted by the API. Though these requirements cannot be enforced on the circuit VM level and do not apply to layer 1 to layer 2 interactions. To let you try out the feature faster, we decided to release account abstraction publicly before fully implementing the limitation checks for the verification step of the account. Currently, Your transactions may pass through the API despite violating the requirements. Assume this will be changed. Nonce holder account. For optimization purposes, both the TX nonce and the deployment nonce are put in one storage slot inside the nonce holder system contracts. In order to increment the nonce of your account, it is highly recommended to call increment min nonce if equals function and pass the value of the nonce provided in the transaction. This is one of the whitelist calls where the account logic is allowed to call contract to call outside smart contracts. Sending transactions from an account. For now, only EIP 712 transactions are supported. Submit a transaction from a specific account. You need to provide the from field of the transaction of the address of the sender, the custom signature, and the custom data. Let's take a look at it. So we import in Zksync Web3. We load the address. Here's the data for the signature. Then we serialize everything and we send the transaction. Awesome. Pretty simple, straightforward. Paymasters. Imagine being able to pay fees for users of your paymasters are accounts that can compensate for other accounts' transactions. The other important use case of paymasters is to facilitating pay fee ERC20 token. While it is the formal fee token in Zksync, paymasters can provide the ability to exchange ERC tokens to ETH on the fly. If users want to interact with a paymaster, they should provide the non-zero paymaster address in their EIP 712 transaction. The input data of the paymaster is provided in the paymaster input field of the paymaster. Paymaster verification rules. The verification rules are not yet fully enforced. Even though your paymaster works at the moment, it could stop working in the future if you do not follow the rules below. Since multiple users should be allowed to access the same paymaster, malicious paymaster can do a denial of service attack in your system. To work around this, a system similar to EIP 4337 reputation scoring will be used. Unlike in the original EIP, paymasters are allowed to touch any storage slots. The paymasters won't be throttled if either the following is true. More than X minute have passed since the verification. Sorry, more than X minute have passed since the verification has passed on the API nodes. The order of slots being read is the same during the run of the API nodes. The first slot whose value has changed is one of the user slot. This is needed to protect the paymaster from malicious users. Built-in paymaster flows. While some paymaster can trivially operate without any interaction from the user, example, a protocol that always pays fees for the users, some requires active participation from the transaction sender. A notable example is a paymaster that swaps users' ERC20 tokens to ETH. It requires the user to set the necessary allowance for the paymaster. The account abstraction protocol by itself is generic and allows both accounts and paymasters to implement arbitrary interactions. However, the code of the accounts UA's content, but we still want them to be able to participate in the ecosystem of custom accounts and paymasters. That's why we standardize the paymaster input field of the transaction to cover the most common use cases in the future. Your accounts are free to implement or not implement the support of these flows. However, this is highly encouraged to keep the interface the same for both UAs and custom accounts. Let's take a look at the general paymaster workflow. It should be used if no prior actions are required from the user for the paymaster to operate. The paymaster input field must be encoded as the following: function generate false data. Okay. The paymaster input field must be encoded as a call to a function with the following: general UA accounts who do nothing and the paymaster can interpret data in any way. Approval-based paymaster flow should be used if the user is required to certain a certain allowance to a token for the paymaster tool. The parameter input field must be encoded as a call to a function with the following signature: approval-based token allowance. The EOA will ensure that the allowance of the token master is set to at least a minimum allowance. The inner input param is additional payload that can be sent to the paymaster to implement any logic. Example, additional signature or key to be validated by the paymaster. If you are developing a paymaster, you should not trust the transaction sender to behave honestly. Provide the required allowance with the example, provide the required allowance with the approval-based flow. This flow serves the most as instruction to EOAs, and requirements should always be double-checked by the paymaster. Working with paymaster flows using the Zksync Web3 SDK. The Zksync Web3 SDK provides methods for encoding correctly formatted paymaster program and for all the built-in paymaster flow. Testnet Paymaster to ensure user experience Paymaster on testnet as well, keeping support paying fees in the ERC20 tokens. The Matter Lab teams provides a testnet paymaster that enable pay fees in ERC tokens to one-to-one exchange, create with if. One unit of token is equal one way of if. The paymaster supports only approval-based paymaster flow and requires the token params is equal to the token being swapped and min allowance to equal at least the X max fee per gas times gas limit. In addition, the testnet paymaster does not make use of the inner input parameter, so nothing should be provided empty bytes. An example on how to use the paymaster can be seen in the quick start tutorial. Signature validation. Your project can start preparing for native account abstraction support. We highly encourage you to do so, since it will allow you to onboard hundreds of thousands of users. Argent users that are already using the first version of Zksync. We expect that in the future, even more users will switch to smart wallets. One of the most notable differences between various types of accounts to be built is the different signature schemes. We can expect accounts to support EIP 1271 standard. The Signature Open Zeppelin library provides a way to verify signatures for different account implementations. We strongly encourage you to use this library if you need to check if a signature of account is correct. Here's how you add it, just to yarn add. And let's see an example of using it. We can get the hash and the signature, and we can verify if that's valid. Verifying account abstraction signatures within our SDK. It is also not recommended to use either.js library to verify for signatures. Our SDK provides two methods with its utils to verify signatures. Let's see the methods. Is message signature correct? Takes in the address, the message, and the signature. Returns a boolean. And is type data signature correct? Takes the address, the domain, type data domain, the types, the value, and the signature. Really nice. So this one is typed. Currently, these methods only support and verify CDSA signatures, but soon they will allow for EIP 1271 signature verification as well. Both these methods can turn true or false, depending on whether the signature is correct.